Hello all, I am Tarun Chandra, 5th year dual degree student from Department of Civil Engineering. Today I am going to present about the topic Machine Learning for Earthquake Forecasting. Let me briefly introduce you about the seminar topic. As we all know, earthquakes cause heavy structural damage and loss to human life. And this is so the focus of interest for variety of fields like seismological research and environmental engineering. Till date, for every earthquake occurred, on an average, around thousands of people have been died. Approximately 1 lakh have been injured and around 2 million have been dislocated. And also considerable number have gone missing or become homeless. Nearly all structure has been destroyed. It has also caused millions of dollars loss to economy. So we can say earthquakes have severe consequences that include not only loss and destruction to living and non-living things, but also significant changes in environment, lifestyle and economy. So if we can able to forecast earthquake in advance, it will get us ready for all worst possible scenarios and will also help us in taking necessary measures beforehand to solve upcoming crises. Predicting earthquakes is one of the important and necessary problems in earth sciences. Although it is one of the problems with immense importance, not many researchers have been done in predicting earthquakes efficiently. The aim of this study is to create a machine learning model for task of forecasting earthquakes. Many seismic monitoring stations have expanded as a result of the increased use of technology, allowing us to employ machine learning and other data-driven methods to predict earthquakes. Our goal is to be able to predict catastrophic events and improve how we respond to them. A warning of impending disaster can be sent ahead of time, which will help to reduce both fatalities and structural damage. For this study of earthquake forecasting, the data collected includes date, time, longitude, latitude, magnitude, depth of past earthquakes as columns. After collecting data, the first step we need to do is data pre-processing. Data pre-processing is necessary because we need to convert the data collected into a clean dataset to make it suitable for use. Data pre-processing involves two steps, data engineering and feature engineering. Data engineering means it involves data integration, computing missing values and taking care of categorical values, transformation and error correction. Whereas feature engineering, a dataset contains a large number of random features that may or may not be useful in prediction. Feature engineering is the process of reducing the number of random features in use and getting a set of minimum features that contribute to accurate prediction. Now I'll explain the methodology of this study. Initially, after collecting the data was cleaned and pre-processed to make it suitable to use in our model. After pre-processing the data, the target variables and feature variables were comprehended and fetched from data. In our dataset, the target variables are the magnitude of the earthquake, whereas feature variables are date, time, latitude, and longitude. Later, the dataset is divided into training and testing dataset. After dividing the dataset into training and testing part, we need to build our machine learning models like random forest, stacking, ensemble, and support vector machine. And we have fitted these models into our training dataset separately. Then the models were used to predict the test data and accuracy of each model was noted. Then the model with greater accuracy needs to be finalized as the best model for earthquake forecasting. As discussed in previous slide, in this study we are going to use random forest, support vector machine and stacking models to forecast earthquakes. First, let us see about random forest. Random forest is a supervised machine learning algorithm. Random forest is also a type of ensemble technique that is based on bagging. The steps involved in random forest are, in random forest and random records are chosen at random from a dataset with k records. For each sample, an individual decision tree is created and each decision tree will generate an output. The final output of the random forest model will be the average of each output of the decision tree. Now let us see about random forest with an example. Here we can see in this figure there is one test sample input, and this test sample input has 600 individual decision trees, and each decision tree will generate us a prediction, like prediction 1, prediction 2, prediction 3, and so on, prediction 600. If we take the average of all these 600 predictions, it will give us one value. The final random forest prediction is this average of all 600 decision trees. Hope the random forest part is clear. Now let us move to support vector machine. Support vector machine is one of the most popular supervised learning algorithms, which is used for classification as well as regression problems. The goal of a support vector machine algorithm is to create the best line or decision boundary that can segregate n-dimensional spaces into classes so that we can easily put the new data point in the correct category in future. This best decision boundary line is called a hyperplane. When predicting a numerical value, support vector machine attempts to find a function f of x in the form of decision boundary at a certain deviation from epsilon, which is the threshold value for all prediction to be within from obtained target's value by a, the original hyperplane, such that data points are within boundary line. This decision boundary is the margin of tolerance, a boundary that allows errors under given range. We can infer the say about the support vector machine model from the below diagram. Here we can see the positive hyperplane and negative hyperplane. This is the margin of tolerance. Now let us move on to stacking. Stacking is an ensemble learning method. Several regression models collaborate. As a result, meta-regressor is built and itself finds its best fit by making use of output of individual regression models trained on absolute training set as meta features. Basically, in this study, stacking is an ensemble of random forest and support vector machine models. Now let us see this figure to understand stacking more clearly. After training each model with our training dataset, we'll predict the new data with our built model. Then each model will give us predictions separately. Like for models R1, R2, and so on Rn, it will give predictions P1, P2, and so on Pn for the new data. Now, if all these models collaborate, a new meta-regressor is built. Then this meta-regressor model will give the final prediction as PF. This is the final prediction of the stacking model, which is the ensemble of random forest and support vector regressor model in our case. This is the bar plot for our random forest model. Here we can see the actual ones were drawn in blue color and predicted ones in orange color. You can see the bar plot for magnitude range versus the data point. Similarly, this is the bar plot for our test data using support vector machine model. You can see this as same as the previous slide. The blue ones are the actual data and the orange one are predicted data. Here is the bar plot for stacking model, which is the ensemble of random forest and support vector machine. Now, finally, let us see the results using our machine learning models. The random forest model has given the accuracy of 74% on our test data, whereas support vector machine model has given the accuracy of 76% on our test data. And the stacking model, the ensemble of random forest and support vector machine, has given the accuracy of 83%. Here we can see the accuracy of stacking model is higher than both random forest and support vector machine. So we can say for our dataset, the random forest support vector machine model works well together when compared to accuracy of each model alone. So the accuracy of stacking model, the highest 83%, is the final one which we are going to apply on our test data. Now let us move on to conclusion part. So we can infer that combining seismic activity with machine learning technology produces efficient and significant results that may be used to anticipate earthquakes in a wide range of situations, provided that prior history of event is sufficiently maintained. Our effort was deemed successful. The machine learning technology can be improved further to better protection against earthquakes. If we have large data sets, then it will be extremely useful. Prediction models can be deployed in an area-centric manner, increasing the chances of accurate prediction exponentially. In our study, we have seen the stacking model, which is ensemble of random forest and support vector machine, has given better accuracy compared to random forest and SVM model individually. However, this comes at an expense of studying the algorithms used to build the stacking model, as it will only perform well if the algorithms used to build the meta-regressor are accurate. The same methodology which we have applied in the study to forecast earthquakes can also be applied to prediction of numerous other natural disasters. So finally, we can say that machine learning technology can be very much useful to predict the earthquakes, and it will help us in the taking necessary measures beforehand to avoid calamities. So this is all about the seminar on machine learning for earthquake forecasting. Thank you.